Okay, this video is to walk you through how to go from a min and max slope and your slope from your graph of time squared versus height, so that's our linearized graph, and to get your value of gravity from that. So based on my data, this is what I got for my min and max slope. My maximum slope was 0.218, my minimum slope was 0.204, and then the line of best fit one was 0.21. This was all for a graph of fall time squared versus the drop height. And I've written that down over here, but I'm going to go ahead and solve this on a piece of paper now. So going through this, what we can see is that my slope was 0.21, my minimum slope was 0.204, my maximum slope was 0.218. To find the uncertainty in slope, I take max minus min and then divide by 2. That comes out to about 0.007, but we're going to round to 2 decimal places because the original slope only has 2, and so does a lot of my data. We showed in previous slides how we got the units for that, but I'm just going to write them there for now so that we know this is absolute uncertainty, which really means that this is about, let's see, 1 out of 20 would be like 5%. So yeah, this is, I think, about like a 5% error, give or take a little bit. Now, from our equation over here, we know that this follows the form of y equals mx plus b, but it goes through the origin, so there's no intercept. So we're going to take our form of y equals m times x, where m is our slope from up here, x is our x-axis, which happened to be height, and then y was our y-axis, which happened to be time squared. And I'm going to plug in those instead of my x and y. So we're coming up with an equation that actually matches what we did. So here we get t squared equals our slope 0.21 plus or minus 0.01 times height is really what this result on the graph is saying. Next, I am going to, I apologize. There we go, I missed a step. Next, I'm going to take a look at my data booklet, and you'll find an equation that looks something like this: s equals ut plus 1/2 at squared. Maybe you remember it from physics 1 looking something like this. That's fine too. But here s is going to be, or d is going to be your height, essentially. It's a distance. U was initial speed, which happens to be 0 because we had everything drop. So that means this entire term out front just disappears. A is the acceleration, which should be our value of gravity. That's ultimately what we're trying to measure here. Now, the reason why I chose this equation is because, well, it has a t squared and it has a distance in it, and it deals with something accelerating, so it makes sense from a theory standpoint that this equation would somehow relate to the equation we derived. And so now we're just going to do a comparison of those two equations. So I'm going to plug in h instead of s or d on the left-hand side, and then we got rid of the ut. So we have h equals 1/2 at squared. From our graph, we remember that t squared times our slope, was equal to our slope times h. So now we're just going to make these two equations look very much like each other and mirror each other so that we can get rid of a few terms and solve for some stuff that's unknown. So here I'm going to move the h over to this side, and I'm going to move the h over to this side so that I get two identical sets right here. So time squared over h, or that ratio, is equal to, and then our slope, or 2 times 1 over the acceleration. Since these two things are now equal to each other, we can actually set these two things equal to each other. And therefore we get 2 times 1 over a equals 0.21 plus or minus 0.01. Remember that a was our acceleration due to gravity. So what we can now do is solve. So we solve for a, and we figure out that the acceleration is equal to 2 over 0.21 plus or minus 0.01. Now, given that this is now in the denominator, and also that it's just being basically multiplied by something, we need to be working with our relative uncertainty. So that should say 4.76% if I'm using the 0.01 rounded. If I use the 0.007, it comes out to like 3 point something% instead. So that means that once I solve for a, this really is 9.52 yada yada yada, plus or minus 4.76% approximately. I take that 4.76%, multiplied by 9.5, and what we get is a value of gravity that is, according to my data, 9.5, give or take 0.5, or plus or minus 0.5 meters per second. Now we know that the value of gravity is 9.8, so 9.8 falls within these results. So cool, I have something that mimics the real world. We actually had a value of gravity of 9.5. That's probably due to some air resistance that was going on based on the shape, mass, weight, all that sort of stuff. But it's there and it's available. Now, to recap, what I did was I plugged in my variables into the trend line. So instead of x and y, I now had the real variables that I was working with. I identified a similar equation from my data booklet. I then identified the given information or information I already knew, such as beginning speed. I rewrote or reorganized both equations to have the independent variable and dependent variable on the same side, because I know those two things should be the same in both cases, which then allowed us to set both equations equal to each other and then to solve for A. So that's the process you can go through to figure out your acceleration due to gravity.